Okay, so we've just, had some notes on the universal law of gravitation. We did an interactive, looking at the different variables that affect how much gravity two things have between them. And we learned that the formula for that was Fg equals big G m1 m2 over d squared, where G is the gravitational constant, which is 6.67 times 10 to the negative 11th, which is always that number, doesn't change. The m is the mass of one object, the other m is the mass of the other object, and d is the distance between them, squared. And that will give you the force of gravity. So when we did the interactive, we moved the sliders around a little bit to look to see how it affected how much gravity you have. We changed the masses and we changed the distance. So let's take a look at that again using the rule of 1. So if we want the force of gravity equal 1, we'll leave G out because that doesn't change anything. And we'll make mass 1 kilogram, the mass 2, 1 kilogram, and the distance between them 1 meter squared. So 1 times 1 is 1, divided by 1 squared still equals 1. So what happens when we decide to double the force? So if we double the force, now it's going to be 2. So the force of gravity would equal 2 times 1 divided by 1 squared. So that would equal 2. So doubling the mass of one object will double the force. And what happens when we triple it? So if we take it 3 times 1 is 3 divided by 1 squared equals 3. So that triples it. If we look at quadrupling it, 4 times 1 over 1 squared equals 4. So that tells me that the relationship between mass and force is directly proportional. If you double it, it doubles the force. If you triple the mass, it triples the force. If you quadruple the mass, it quadruples the force. So that was one of the things you were supposed to take away from the interactive. And then obviously if you double the other one, it is also going to increase the mass. So anytime you increase something on the numerator, it's going to increase the answer. Well, let's look to see what happens if we increase the distance between them. How does that affect it? So if we leave the masses both 1, and now we double the distance squared, right? So 1 times 1 is 1, divided by 1 squared is going to make it 1/4. So that decreased it 4 times. If we triple the distance between them, so that becomes 3 squared. So 1 times 1 is 1, divided by 3 squared is going to be 1/9. And if we quadruple the distance between them, so it's 1 times 1 divided by 4 squared is now going to be 1/16. So we see if you increase the denominator, it will decrease the answer. So that's an inverse proportion. And it has a square, so we call that the inverse square. And so if we double it, it becomes 4 times less. If we triple it, it becomes 9 times less. If we quadruple it, it becomes 16 times less. And if we take that on, if we said that if we made it 5 times farther away, it would be 1/25, and so on. So those are the kind of relationships that we should have gotten from our interactive we did the other day. Changing the mass is directly proportional. Changing the distance is inversely proportional. All right, so now we're going to work a couple problems with numbers. So here's the first problem. We got Mars has a mass of about 6.4 times 10 to the 23rd, and its moon Phobos has a mass of 9.6 times 10 to the 15th kilograms. And if the magnitude, that means how much, of the gravitational force between the two bodies is 4.6 times 10 to the 15th newtons, how far apart are they? So we are looking for the distance. So if we take our formula, Fg equals G m1 m2 over d squared. So we have rearranged some problems before, and we talked about cross multiplying. If we take a value that's on the denominator and we move it across the equal sign, it becomes in the numerator. So d squared would go up to the top, and that gets rid of it. And if we move Fg across the equal sign, it's going to move from the numerator to the denominator. So Fg would go on the bottom, and we would be gone here. And so we got d squared equals G m1 m2 over Fg. And then remember, we're not going to solve for d squared, we're solving for d. So you'd need to take the square root of that, and you must do the same thing on both sides of the equal sign. Now once we have that, we can plug in our numbers. So we have d equals the square root of 6.67 times 10 to the negative 11th times 6.4 times 10 to the 23rd times 9.6 times 10 to the 15th. And then all that's going to be divided by the force of gravity, which is 4.6 times 10 to the 15th. All right, so it's a lot of numbers there, and we haven't done anything with exponents in a while. Now, unfortunately, I didn't bring a calculator home, like many of you probably have not either. So we have to use something on our phone. There is on your computer a calculator app that you can click from the home screen, and it will give you that. If you'll click it, you check up to the top and make it into scientific calculator, and it'll give you the same kind of screen this is. So this one's a little different than what we did at school, where normally we would hit the square root number first, plug in all your numbers, use parentheses. Well, this one didn't quite work that way. So you're going to take 6.67, you're going to hit the double E button, and you're going to take 11 and then hit the negative sign, which is different in our calculator where we would hit the negative, then hit the 11. All right, so once you got that, you'd multiply by the next number, 6.4 double E 23 times 9.6 double E for the exponent, and then 15. And I went ahead and hit equal. And then I'm going to divide that by the denominator, which is 4.6 double E, and then 15 is the exponent, and then hit enter. Now we have to do one more step. We have to hit where it says 2 square root of x. That's going to take the square root of it. So we'll hit that button, and we get an error. Well, let's try this again. There, that worked. I don't know why we got an error the first time. So it's going to be, it won't go in scientific notation because this calculator won't do it like our other one will. So it's going to be, remember, take the first two numbers. So we got 9.4 times 10. And if we count the decimal places, we go 1, 2, 3, 4, 5, 6. So 9.4 times 10 to the 6 newtons. So that's the answer to the first one. All right, let's take a look at the next one. We got find the magnitude of the gravitational force of a 66.5 kilogram person would experience while standing on the surface of each of the following bodies. So we're going to look at the Earth, and then we're going to move that person to Mars, and then we're going to move them to Pluto. Now, we should know, because the mass is decreasing for each of these, from what we talked about earlier, the force of gravity on each of them should go down. So if we decrease mass, we should also decrease the force. So let's see if that works. So we're going to take our formula. We know that it's, let's see, Fg equals big G, m1, m2 over d squared. All right, so we'll plug all that in. 6.67 times 10 to the negative 11 times 66.5, so we'll use that every time, times the Earth's mass, which is 5.97 times 10 to the 24th. All that will be divided by the radius, or the distance between them, 6.38 times 10 to the 6th, and we got to remember to square that. Now, when we plug this in the calculator, it won't allow us to put the parentheses in here to do the square at the end. So what you will do is you'll do, multiply everything that's on the numerator, divide by the number on the denominator, and then divide again by that number because it's squared, and that will give us the correct answer. So let's take a look at that. All right. So move this over. All right, so we're going to go take the universal law of gravitation number, it's a constant, it's going to be 6.67, second function, EE, and then it'll be 11 negative times 66.5 times 5.98 EE 24, and then hit enter. And then we're going to take this denominator and divide it 2 times. So we're going to divide by 6.38 EE 6, get an answer, and divide it one more time, 6.38 EE 6, and we don't get the right answer. So let me go through it again and see if we get the right answer. Weird, I must have hit a multiply instead of divide the second time around. So the force of gravity is going to be 650.5 newtons. You could round that to 651, which is about right for a person that weighs that much on Earth. Remember, the kilograms are always smaller than pounds. So this person's probably like 140 pounds. And then the newtons are always much bigger than kilograms. That's why we don't use Newton scales. Everybody thinks they weigh too much. All right, so we're going to do the same thing again for the next 2 problems. And as we see, the masses are going down because this is 10 to the 23rd, so we should have less of a force. Also, now the radius gets a little bit smaller, so remember that affects it a little bit. So it should go up a little bit. So between those two, we should get a smaller number because Mars is smaller than the Earth. And then we'll do the same thing with Pluto and see if we get another smaller number. All right, so FG equals, this number is always going to be the same, 6.67 times 10 to the negative 11. We still have the same person, so 66.5 kilograms, but times the new mass, which is 6.42 times 10 to the 23rd. All that's going to be divided by the radius of the planet, which is 3.4 times 10 to the 6th squared. All right, so we'll plug all that in and see what kind of answer we get. So 6.67 EE 11 negative times 66.5 times 6.42 EE 23 equals that, divided by 3.4 EE 6 equals that, and divide it one more time by 3.4 EE 6. And as we see, we get 246. So it is smaller than what it was on Earth. All right, and then we'll do the same thing with Pluto, and it should be even smaller. So FG is going to be big G, which is 6.67 times 10 to the negative 11, times the same mass. And this is going to have even smaller mass for Pluto. It's 10 to the 22nd. And all that's going to be divided by a smaller radius, which is 1.2 times 10 to the 6th squared. All right, cancel that out. And we go 6.67 EE 11 negative times 66.5 times 1.25 EE 22 equals this, divided by 1.2 EE 6, and divide it one more time by 1.2 EE 6, and we get 38.5, which makes sense because Pluto is a much smaller mass. All right, so it should be fairly easy to pick out the variables, and then you just have to be able to plug in the right numbers. And the only other part where you could have problems, which I did, was hitting multiply or divide. Make sure you hit the exponent key to get those. All right, so let's look at the last two. Like this one would be something like every day. Like we want to see what the force of attraction is between two people sitting in a desk at school, or how far apart they are. So they give us the force of attraction between them is 3.2 times 10 to the negative 8, which makes sense. And we're not all getting attracted to each other across the room because it's a very small number. And then the two masses of 50 and 60, that's about average for people. And we want to know, well, how far apart are they? Like, you know, how far apart are their desks? Let's see if that makes sense. So we got FG equals big G again, M1, M2 over D squared. So we're trying to find D squared. We don't want a denominator. So if we move it across the equal sign, remember it goes diagonally up. So D squared would go at the top. And then FG we don't want at the top, so it's going to move down to the denominator, basically switching places, and we're left with this. And we don't want d squared, we want d, so we take the square root of both sides, and then we'll plug in our numbers. So d is the square root of g, which is 6.67 times 10 to the negative 11. And then this is easy, we just get 50 kilograms and 60 kilograms. And all that will be divided by the force, which is 3.2 times 10 to the negative 8. So think about how far apart you guys sit in class. And think about that in meters and see if we get close to what we think it is. All right, so we're going to take 6.67 EE 11 negative times 50 times 60 equals this. And then we're going to divide that by 3.2 EE 8 negative, and we get this, and then we take the square root of that, and we end up with 2.5 meters. So some of you guys sit right next to each other, which is obviously less than a meter, but in the rows that have the aisle between it, you probably are about 2.5 meters apart. So close to 8 feet. So that does make kind of some sense there. All right, the last one, we're going to talk about something that's really small. So we have really small exponents here. We want to know what is the force of gravity, or the Fg, of an electron, which has 9.11 times 10 to the negative 21 kilograms, and a proton, which has 1.67 times 10 to the negative 27 kilograms. So these are really small things. And their force of attraction between them is super small. It's 1 times 10 to the negative 47. So it's really, really small. So you could probably think with all these small numbers, we're probably going to have a distance that's really small. So we're looking for distance just like the last problem. So I'm just going to copy what we used before. D equals square root of G, which is 6.67 times 10 to the negative 11, times the mass of the electron, which is a 9.11 times 10 to the negative 31, times 1.67 times 10 to the negative 27, all divided by the force of gravity between them, which is 1.0 times 10 to the negative 47. All right, so let's plug in our numbers. 6.67 EE 11 negative times 9.11 EE 31 negative times 1.67 EE 27 negative equals this really small number, 10 to the negative 67. Then we're going to divide that by 1.0 EE 47 negative equals this number. And remember, we got to take the square root of everything. Something doesn't look right. So I'm going to redo it again. I must have missed the number somewhere. Well, if you get the number the same twice, that's probably the right answer. Maybe I was wrong the first time I worked this. So it's going to be 1.0 times 10 to the negative 10th. And that's going to be meters. So really small distance, which makes sense. They're inside of an atom, so it's really small. All right. So that is how you work problems. And what I'm going to do is also put on your, for tomorrow's problems to work are going to be these, universal law of gravitation. So you got about 13 questions. Some of them are just going to ask questions, and some of them are going to work some problems. Some of them are going to talk about the relationships between stuff, which we did at the very beginning of this video. And so you'll do the rule of one for that. And so I want you guys to, you should be able, well, you're probably going to have to print these off, write the answers out, and then take a picture and send it to me like the other ones. I know it's a hassle, and trust me, I've been trying to find easier ways to making this, be able to present this material. If there's an easier way in the next week or so, we'll learn as we go. I'm also going to put this on a new site instead of the YouTube. It'll be a YouTube video, but it's going to be on safetube.net or something like that. But I'll have the link on there, and you shouldn't have a problem accessing that. So like always, if you got questions, go ahead and email me the question through Schoology. Remember to submit your stuff. Some of you are doing a great job of submitting the answers. I'll start putting some grades in for you guys that have actually submitted something to me. And then we'll probably do a Friday, we're probably going to do a quiz on the vocabulary, so make sure you're looking over that. I'll probably put a Quizlet up so you guys can practice, or maybe we'll try to put up a time that we can do a Quizlet live during our office hours and see if that'll work. And then I'll try to put the quiz on Schoology. I'm going to try to figure out how to do that. If I can, we'll do it. If not, we'll figure out something else. All right. Hope everything's going well for everybody. I'll talk to you guys later.